Hello everyone, this is the fourth video of this series, and in this video I am going to show you how to make a active filter. Actually I am going to show you active filter only, because if you are able to make an active filter, you can make the passive filter yourself. So I am going to make an active filter using op-amp. Basically I will be making a RC low pass filter of first order with R equal to 1 kilo ohm, C equal to 1 nanofarad. So our cutoff frequency will be approximately 159 kilohertz. So let me search the schematic. Okay, so see, I click here and I search op-amp. So if you search op-amp, you get a number of options. These are various op-amps. For example, this is LM324, which is commonly used for comparator applications, and for analog circuits we normally go for MU-A741, and we are going to use the same op-amp, the MU-A741, for this particular experiment. Let me slightly zoom in so that you can see properly. Okay, so for this what we need the biasing voltage PDC. Let's need 2 PDC. Just connect them. Let's say this is 12 volt and this is also 12 volt, and in between we have the ground. In between we give the ground, and we can, this is the, so we have done the biasing basically. Okay, so from this circuit, from the, this is just like a dual power supply, plus 12 and minus 12. In between I have made this ground, so this will be plus 12 volt and this will be minus 12 volt. Now let's first use this phi sign, because as I already told you, phi sign is basically used for making transient analysis, but just I am going to show you what happens if we use phi sign. And we need the R and C, so I need the resistor which is 1K. This is the resistor 1K. This is low pass filter, so the resistor will be in series and capacitor will be in parallel. So I am just setting the default values. Okay, so I am just making a I will simply connect it to non-inverting terminal. It is very simple. And this is connected to a ground. So basically A, Z and D, and this is connected to the ground. Okay, so I have to give a feedback part from pin number 3 to pin number 2 to pin number 6. So let's say okay, so this will not, this I'm sorry, this is wrong. So pin number 2 will be connected to this. So let's say the gain of our op-amp is, okay, let's say all the resistors are 1 kilo ohm, just to make it simple. So from pin number 6 we have to connect this feedback part. From here it goes here, from here we have to pin number 2, and this is connected to ground again. Okay, so this is the inverting part. The gain is given by 1 plus RF by R1. So this is R1, and let me just tell you, this is R, this is R, this is R1, so this is RF, and this is R1. So I am using the standard notation. So the gain is given by 1 plus RF by R1, which is the non-inverting amplifier, and I have this feedback part, and the low pass, the passive filter is connected to the non-inverting terminal of the op-amp. So this is how it works, and I have to again give a load resistance. so R, so another resistor, so another resistor. I can directly connect it here because this is also connected to pin number 6, and I need again a ground. So this is suppose our load resistance. Let's say this is, let's say 2K. Okay, so this is the basic filter. I'm not going to use any offset null, and that's all, right? So let's do the simulation. Before that, I have to set the parameters. Our offset voltage is 0, and amplitude is suppose 1 volt, and let me show you. Let me set this frequency because so offset should be 0. Offset is 0. Save. Amplitude is 1 volt. Save, and frequency. See, our cutoff frequency is approximately 160 kilohertz, right? And this is a low pass filter. So first, let me give you some frequency which is less than this. Let's say 50 kilohertz. Let's say I give a frequency of 50 kilohertz. 50 kilohertz. Okay. So this is 50 kilohertz. And now I do the transient analysis, transient setup. So I give the transient setup. So as you can see, if our signal is 50 hertz, 50 kilohertz, that means what should be the, so just calculate and see. If our it is 50, f equal to 50 kilohertz, that means T is 1 by f. So T is 2 into 10 to the power minus 5. That means 200 microsecond, right? 20 microsecond. Yes, 20 microsecond. So let me just make it 100 microsecond, so that we have some 4 or 500 microsecond. So for micro we write U, because mu is not there in the keyboard, so I write U for micro, and close. And we can press this button simulate to start the simulation. So I have to save this. Let me make a new folder. Sorry. Let me make a new folder which is LPF, suppose LPF, and see what happens. Okay, so simulation is done. So let me just see the, I'm not going to plot the current, I'm just going to plot the voltage V. What is this resistance? This is R4. R4 is the load resistance, right? So I am going to plot the voltage across R4 is to 1 and R4 is to 2. Let's plot these two, and you can see R4 is to 1 is 0, because that means this side, this is the R4 is to 1, this is the terminal 1 which is connected to ground, and R4 is to 2 is connected to this part, that must be number 6. So we see our amplitude is 1 volt, right? And this has a gain of 2, because 1 plus RF by R1, RF and R1, these two are same. So the gain of this circuit is 2. So I am giving a 1 volt signal, and I am getting a 2 volt output. So this is basically acting like an amplifier at a frequency which is much less than the cutoff frequency of the circuit, right? Again, we can see that we have exactly five number of waveforms, because we have set the time accordingly. Now let's increase this frequency. Let's make it something bigger than 50 kilohertz, because our cutoff frequency is 159 kilohertz. So let's make it something bigger than 159 kilohertz. Let's make it suppose 200 kilohertz. So if I make it 200 kilohertz, and again we run the simulation, and I am not going to plot the current. R4, VR4, I just want to plot the VR4. VR4 is to 2 because pin number 2. So you can see now the signal does not look nice, right? Now the signal does not look nice because it is highly attenuated. The amplitude is much smaller. This is VR4 2. If you look at VR4 is to 1, it is still 0 because this is pin number 1 which is connected to ground, and this is pin number 2 which is connected to R4, and it is highly attenuated because we are far beyond its cutoff frequency. We are getting something which is much less than 1 volt. So this is like a transient analysis, but if we want to do a frequency domain analysis of this circuit, we have to change this input. Let's delete this. I just press the delete button, and now I give a VAC, right? VAC, and I replace it VAC. So see, for this VAC here I only have to set the voltage. Let's say the voltage is 1 volt, and going to set up, I have to unselect this. We are no longer going to see a transient analysis, but we are going to see an AC sweep. So there are these are all the sweeps. So normally we can octave and decade. So we have these are octave and decade. These are logarithmic sweeps. So we are going to see the logarithmic sweep, so decade. This is the semi-logarithmic plot that you see. So let's say our start frequency, we start from, say, our cutoff frequency is 159 kilohertz, right? So let's start it from 1 kilohertz and go up to, say, 10 megahertz, 10 capital M. Okay. Okay, there is an invalid value because I remember if you go to setup AC sweep, so this cannot be 1 meg, it should be 1 MEG, right? Mega means MEG, because actually this PSPICE does not differentiate between capital letter and small letter. So if you just write M, then it gets confused between milli and mega. So this mega is always written as MEG. So now we are ready. So at this, again I am going to see the, I am not going to see the full current, I am just going to see the voltage. PR4 is to 2. So you can see here, this is 100 kilohertz and here it is 2 volt because our input is 1 volt and gain is 1 volt. So this is 1 volt and it slowly gets shifted. So, and again we are not going at dB, we are not doing this analysis at dB scale, we are just looking at the voltage. You can manually convert this to voltage if you want, to dB if you want, and but we can get the waveform, the frequency analysis of the circuit directly from this simulation result. So this is how it works. So I think you have understood how to do a frequency domain analysis using op-amp, using this PSPICE. So this is the op-amp, and in a similar way you can make any circuit and do a frequency domain and time domain analysis using PSPICE simulator. So thank you.